This video is 2.4 Algebraic Reasoning. In Chapter 2, we've been talking about different types of reasoning, we've been talking about conditional statements and how to use those. And so in this one, we're actually going to be starting to apply it even more to math. And suppose first we're going to start looking at just the algebraic part, algebra that you should have been doing. We're going to look at how you justify each step, and then the different types of properties you use in order to justify. And then we can also start to look at some segment lengths and some angle measurements as well. So when we think of solving an equation, a lot of times we can look at our different types of properties that we have. So many of these we use, we don't necessarily know what properties they are, or we just don't think about them. But if we use these letters of A, B, and C as real numbers, so it says let A, B, and C be real numbers. Then if we look at each of these properties, so first one is addition property of equality. So if A is equal to B, then A plus C would be equal to B plus C. So think about it, if I have A is equal to B, well obviously if I add the same amount to either side, it will still be equal to both sides. Okay, and notice these are written as conditional statements. Then our second one is very much like addition. So if A is equal to B, then if I subtract the same amount from either side, then it would still be equal. So here they subtracted C, and then they subtracted C, so A would still be equal to B. Multiplication property of equality. If A is equal to B, well then if I multiply the same value to both sides, then A would still be equal to B. This only applies though if C is not equal to 0. Division property of equality, if A is equal to B, then if I divide A and B by the same amount, again of C, then I still would have an equal equation. So C is still cannot equal 0 though. I cannot have 0 in the denominator. And then I can have substitution. So substitution, if A is equal to B, then A can be substituted for B in any equation or expression. We do this a lot of times in algebra. You know, if X is equal to 2, well then I need to plug it back in to find whatever my value was, whatever I'm looking for in the problem. So when we look at this problem, we are going to be able to create a table for it. We are going to have our statements and we're going to have our reasons. So on the left side, first I'm going to start with this equation that I was given. So I have 3x plus 2 is equal to 23 minus 4x. That's my first statement. My reason for this can be that it was just given to me. It's my first one. So then I'm going to work my problem like normal on the left, but I'm going to be telling how I'm doing it. What is my reason for being able to get to that step? So we can know from looking at this, I need to combine like terms. So first, to combine like terms, I'm going to first try to get my x's together. So I'm going to add 4x to both sides. So my new statement would be 7x plus 2 is equal to 23. So to get there, my reason for this statement would be addition property. I added the same amount to both sides. And then I'm going to go ahead and number these so we can see this was my first statement, this was my first reason, this is my second statement, this is my second reason. So then I still need to combine like terms as well. I need my 2 and my 23 together. So I need to subtract my 2 across. And so when I subtract from both sides, I end up getting 7x is equal to 21. This is my third statement. And then my third reason to get to that step, I had to subtract. So this one would be subtraction property. So I still need to get x by itself. So in order to do that, I need to get rid of the 7. So I'm going to divide by 7 to both sides. So I end up getting x is equal to 3. And so my reason for this would be division property. And so I solved for x, so this would be my final. But this whole thing is my answer. It's not just that my answer is x is equal to 3. I was asked to justify. So on this right side, my reasons is my justification. So then we still have more properties. We also have distributive property. Remember, distributive is when I'm going to multiply inside the parentheses. So I'm going to multiply this a to all terms inside to get a, b, plus AC. And this works the same way. If I'm subtracting, I multiply this A to both terms. So if I was subtracting those terms inside the parentheses, it would be AB minus AC. So we have this second example. We want to use distributive property. And so we need to justify each step, just like last time. So I'm going to go ahead and move this up so I have more room. So once again, I need to have a table. So I need to have my statements and my reasons. So I just make a T-chart. Anytime I start, my first statement is going to be what I was given. So I have negative 5 times 7W plus 8 is equal to 30. My reason for this, I haven't done anything, so it is just that it was given to me in my problem. And now I need to solve, and once again, I'm going to put my reasons on here. So my first step, I have this negative 5 outside of my parentheses, so I need to distribute this inside. So if I multiply negative 5 and 7, I get negative 35. W, negative 5 times 8, I get negative 40. And it's still equal to 30. Once again, I can number my statements versus my reasons, so that way we can stay on track here. So my second reason, it pertains to what I just did. So in order to get the second step, I had to distribute. So that would be our distributive property. Now I keep solving. So I'm going to try to get my like terms together. I already have all my W's together, but I need to get my numbers. So I need to add 40 to both sides to get my new statement of negative 35 W is equal to 70. This would be my third statement. And so my third reason to get to that step, I had to add, so that would be addition property. I still don't have W by itself though, so I need to divide. So I'm going to be dividing by negative 35 to both sides. And so 70 divided by negative 35 gives me negative 2. This is my fourth statement. And so to have gotten to that step, what we did was we divided. So this would be division property. So that would be our statements and reason. Once again, this whole thing is our answer. So then we still have a few more properties we need to go over. First one would be reflexive property. Reflexive property simply tells me that if A is equal to A, okay, so if something is equal to itself, well then of course, that would just be reflexive property. I can assume if they are the same, then they're going to be equal to each other. Symmetric property is A is equal to B, then B is equal to A, so it simply just tells me I can flip it around. I can switch things on either side of the equal sign. And then transitive property tells me if A is equal to B and B is equal to C, then I can eliminate this middle portion and just say that A is equal to C. Okay, I can come to that conclusion. Remember, that is like what we talked about with deductive reasoning. So if I have that same conclusion versus that same hypothesis, I just kind of take out the middle portion. Same thing goes for transitive property. If A is equal to B and B is equal to C, then I can go ahead and say that A is equal to C. So now we have a problem that pertains to angles. So this gets more into our geometry using the properties we've been talking about. So we reflect a beam of a spotlight off a mirror lying flat, and we want to determine whether DBA is equal to the measure of EBC. Okay, so if we look at this, DBA is going to be this angle here. Yeah, so I'm putting it in green. You could also mark it by one line versus two lines. And then EBC is this angle going here, going the other direction. Okay, so they both share this common angle of 2 in the middle, but one of them has angle 1 in it and one has angle 3. Okay, so we're going to go through this and we need to do our T-chart again in order to show whether or not these are equal. So I have my statements and my reasons. So first, I'm only given a few things. I'm given in this picture, so I can look at this picture and that's what I'm going to start with. So in this diagram, first I can see that 1 and 3 only have one line on them. So that would mean that those angles are equal. So I'm going to write that angle 1 is congruent with angle 3. This would be a given because it was given to me in my picture. Something else I can see from this is that angle 2 is the same, okay? DBA and EBC both share this angle 2, okay? Well, angle 2 is going to be equal to itself, so I could write out that angle 2 is congruent to angle 2, which would be our reflexive property. But in order to determine whether or not these are actually equal, I need to try to figure out something about the total. Okay, so we know a total, whenever we're looking at it, the total is equal to its parts. So if I were to add the parts, it would give me the whole. So the measure of dBA would equal measure of angle 2 plus the measure of angle 3. The measure of EBC would equal the measure of angle 2 plus the measure of angle 1. And the reason for both of these would actually be angle addition postulate. So if I'm looking and if I want to try to determine whether or not they are the same, then I could possibly look at substituting here. Okay, if I have angle 3 in this first one and I have angle 1 here, let's try to get them in some of the same terms. So I'm going to go ahead and substitute, and for angle 1, I'm going to put in this angle 3, because up here we have that it is congruent. That's something that was given to us, so that means their measures are the same. So I can write out that the measure, instead of EBC, is equal to the measure of angle 2 plus the measure of angle 3. And so that would be substitution property. And then the last thing that I'm going to do is I'm going to look at if something is equal to the same thing. Here we have measure of angle 2 plus measure of angle 3. Here we have measure of angle 2 plus measure of angle 3. If they are equal to each other, then I can set them, whatever these two parts are. It's kind of like substituting. But if they're both equal to the same thing, then I can set them equal to each other. So here I'm going to write out that the measure of dBA is equal to the measure of EBC. And I will rewrite this up here at the top. Okay, and this will be the transitive property. Okay, so if you couldn't read that up here, all I wrote down was I had the measure of dBA is equal to the measure of EBC due to transitive property. Okay, that's all that part says. So I got to what I was trying to determine right here. This is what we're trying to prove it. I reached that conclusion, so yes, it would be true. We determined that dBA is equal to EBC. So then we have one more problem. We're going to look at one that's kind of applies to segments now more than angles. We're going to be looking at segments like a real life situation, kind of being on a street. So we have a park, a shoe store, and a pizza shop and a movie theater that are located on a city street. The distance between the park and the shoe store is the same as the distance between the pizza shop and the movie theater. Show that the distance between the park and the pizza shop is the same as the distance between the shoe store and the movie theater. So they told us that they're located in order. So first we want to draw this picture. So we have a street. It says we have a park first. It says we have a shoe store I'm just going to write shoe. We have a pizza shop, and we have a movie theater. It tells us in our little statement here, the distance between the park and the shoe store is the same as the distance between the pizza shop and the movie theater. So the park and the shoe store, so I'm going to put a tick mark here. And then between the pizza shop and the movie theater, so a tick mark here. And it wants us to show that the distance between the park and the pizza shop is the same as the distance between the shoe store and the movie theater. Okay, so again, we need to use our proofs. So we need to make our statements and our reasons. And to make this simpler, I'm going to go ahead and just give these points names. Instead of park, shoe, pizza, movie, I'm going to give them actual point names with the letter. So the park I'm going to do is P. The shoe store I'm going to do is S. Pizza I'm going to do is Z since it has so many Z's in it. And then movies I'm going to do it as M, point M. Okay, so in my statements, first I'm given that I have the park to the shoe store and the pizza to the movie are the same distance. So that would be segments PS is equal to ZM. Okay, their lengths are equal. They told me the distance is equal. My reason for this would just be given. So I need to start thinking about what I'm looking for. I'm looking for whether or not PZ is congruent to SM. Okay, so I'm right here. I'm just going to write PZ equal to SM. Okay, that's what I'm looking for. I'm going to put that question mark there. So if I'm looking for PZ, I need to know what makes PZ. So I'm going to go ahead and write that PZ would be equal to its parts. Okay, so if PZ is the total here, I can get to Z by jumping to S and then going to Z. Okay, I'm going to add my parts to make my whole. PZ would equal PS, if I go to the shoe store first, plus SZ. My parts make my whole. This would be segment addition postulate. Then we're also looking for whether or not PZ is equal to SM, so I need to think about what makes up SM as well. So SM would equal its parts as well. So going from S to M, I could jump there, so I go first to Z, then to M. So I have my two parts there. So it would be SZ plus ZM. This one would also be segment addition still. And so now, once again, I have these statements, okay, and I have something where maybe I can substitute. So I have PZ and SM. I want to try to get them in the same terms. So notice here we have SZ in both of them. So I need to get the other two on the same types of terms. Well, notice that they were equal to each other up here. So I'm going to go ahead, instead of ZM, I'm going to plug in PS in that second statement. So I'm going to have SM is equal to SZ plus, instead of ZM, I'm going to plug in my PS. And this is substitution property. And so now notice that SM is now equal to SZ plus PS. PZ is equal to PS plus SZ. Those are the same things. So if PZ and SM are equal to the same, then that means that they are equal to each other. So PZ is equal to SM. This once again would be transitive property. And so we proved that PZ is equal to SM. So we are done. Okay, proofs, as we start to get into this reasoning, and we move more into what do we call proofs here like this, try to not get frustrated. It sometimes can be hard, but just keep working and keep trying to look and reason and try to find these. Sometimes your table will not necessarily be in the same order. I could have switched some of these. Okay, I could have had substitution property differently down here. I could have substituted in the PZ statement. Okay, sometimes they can be in a different order. Sometimes you can have a few different steps, but you just need to be showing your steps to get to the same conclusion. To get to that conclusion, in this case, that PZ was equal to SM. So the distance is the same.